Okay. So, I'd love to give you time to practice that, but you can do that at home tonight. Okay. And you guys are going to get one of these and one of these. The extras for equilibrium are much smaller than like the extras for other units, so I just stapled it this time. Okay? One of each of those. Don't take my grade 9 test. There's no more answers? We ran out of answers? Oh, look, more answers.
I just realized that I forgot to pay the work with you told me to.
You can totally do that, yeah, yeah. Alrighty. 2.5a, page 1. KC. KC is just another word for KEQ. The C stands for concentration. So in our K term, we are using, guess what? Concentrations. Does it look any different than KEQ? No, because it's the same. Okay? Did you like learning that? That was awesome, right? So if you see KC, you just think KEQ. KC is independent of concentrations. What does that mean? If you stress the system by changing concentration, the system will by the way, that delta, changing. Yes? Lazy, Ms. Spence, changing. If you stress the system by changing the concentration, what will the system do? Tell your partner. Is it going to stay the same or is it going to shift? You have stressed a system. What's going to happen? It's going to shift. And it's going to shift until the ratio of products to reactants once again equals Kc, i.e. Keq. Does that make sense? What's happening is that Kc will not change when you change the concentration. If you stress the system by changing the concentration, you no longer have equilibrium ratio, so you have a Q value, yes? Right, you're not at equilibrium, it's going to shift back to an equilibrium where the ratio is the same. Kc depends only on temperature, because if you stress a system, by changing the temperature, what will the system do? If you stress a system by changing the temperature, the system will shift, has to shift, you've stressed it. And the ratio of products to reactants will change. So there's nothing new, it's just making you think about it in a slightly different way. Yes? If you find that confusing, have a little chat about it. Have a little think on it. Now, how does Kc relate to kinetics? I feel like you're never going to have to do this. I don't think this will show up on an AP exam. So we're going to go through it quite quickly, and you can maybe just ignore it if you don't want to learn it, okay? So consider the following elementary reaction. We've got two particles on the left, and we've got two particles on the right. Yes? Okay, so the rate of the forward reaction, because it's an elementary process, if it's an elementary process, we can use the coefficients as exponents. Yes, this is from rate law. Are you remembering this? How do you find the coefficients otherwise, if it's not an elementary process? By experiments. Okay, but here we go. We've got this here. And we have H2 and I2. They both have a coefficient of 1, so the exponents are 1 and 1. Yes? Now, the K of the forward reaction, the rate constant is K forward, and we have the rate constant of the reverse reaction, K reverse. And when we are at
equilibrium, what do you know about the rate of the forward reaction and the rate of the reverse reaction? They are the same. So this is equal to that. So what we're going to do is we're going to take this here, we're going to take this here, and we'll say those two things are equal because that's the rate of the forward reaction is equal to the rate of the reverse reaction. So far, so good? Okay. Now, let's rearrange it. So we're going to take our products and keep them on the top. Yes, there's our products. And we're going to take our reactants and put them on the bottom. Yes, so now we have products over reactants. Right, we got our products over our reactants. And what do we have if we have products over reactants? That's equal to Kc, which is also equal to Keq. And what that also means is that Kc is equal to the rate constant for the forward reaction divided by the rate constant for the reverse reaction. Yes? Now, how likely do I think this is going to come up on an AP exam? Not at all. So you can just be like, okay, that's nice. Woo, moving right along. But it does prove that, you know, kinetics does relate to equilibrium and equilibrium does relate to kinetics. How does Kc change when the equilibrium equation is manipulated? So let's start by reversing the direction. Okay, so we're going to reverse the direction. So my reactants have become my products, and my products have become my reactants. Yes, we've just switched the direction. So here we have NO2 squared is on the top. Here, NO2 squared is on the bottom because we've just switched them. We have NO and O2 on the bottom because they're reactants. Now they're products, so they're going to go on the top. So what is the relationship between this thing here and this thing here? How do those two relate to one another? The two red boxes? They're just the inverse, the reciprocal, yes? So you just flip it. So if you reverse a reaction, you just flip your Kc. So if we had a Kc value for the forward reaction, Kc is 4.67 times 10 to the negative 13, then Kc, and we're going to call it prime. Okay, that's how we distinguish it. It's like we've done something to Kc now. Yes, we've reversed the reaction, so we're going to flip it. So this Kc prime, in this case, it's for the reverse reaction. It's equal to 1 over Kc, and then you just take the number, and you get your final answer. Is good? How do we feel about that? Okay, so if I give you a value for a K, for a forward reaction and then I reverse the thing, you're just going to flip the number. You're going to do 1 over whatever the Kc value was. Yes?
You know what? It works for all reactions. Don't ask me why. If it's not like complicated things, I just am like, it works because. Yeah. So this works for all reactions.
At least all reactions we're dealing with in chemistry 12 and AP chemistry. So here's our first box. Our second box. Why is that way up there? That's really weird. I don't know. Anyway, this is like, move this. Move this. It wasn't supposed to be like hanging out here in the middle of nowhere. So let's take a look at our reaction. We have a coefficient of 2, a coefficient of 1, and a coefficient of 2. And we know that Kc is, we have a 2 and a 1 and a 2. Let's take our reaction. If the coefficients are all multiplied by a half, so that's what's happening here. I don't know why it's way up there. It should go like down in here somewhere. Yes? But if you multiply them all by a half, you get 1, and you get a half, and you get 1. Does that make sense? Okay. If we multiply them by a half, then the exponents are also multiplied by a half. Okay? So what you can see is that we have now NO2 to the 2 times a half. That gives us NO2 to the 1, which, oh look, we have a 1. Yes? Okay, we have NO to the 2 times 1/2, which is 1. Oh, look, we have a 1 there. And we have O2 to the 1 times 1/2, which is equal to 1/2. Yes, and guess what? We have a 1/2 here. Yes? So what it means is that the Kc, and in this case, again, we call it prime because we've done something to it. The prime indicates we've done something to the reaction. We might be flipping it, we might be multiplying it by a half, we might be doing some combination, who knows? So you don't need to actually show all of this work, you just need to know that if you multiply the coefficients by 1/2, then you are going to raise Kc to the 1/2. Yeah? And so you say, okay, I've been given a value for Kc, so I'm going to raise it to the, oops, this should say 1/2. I left this out, make sure you write it in. Okay, make sure you put that half there, and of course a half is the same as a square root, so you can use whichever button you want. You can use x to the 1 over y, or you can use your square root button, and you get your final answer. Is good? Okay. So if you multiply the coefficients by n, you raise kc to the power of n. So if you multiply the equation by 3, you raise kc to the 3. If you multiply the equation by half, you raise kc to the half. And this is the only one that might be a little bit tricky, but it's a lot like Hess's law, okay, or reaction mechanisms, because we're adding reactions together. So here we have step 1 of our reaction mechanism. We have an NO2, and in our overall reaction we have an NO2. Yes? In step 1 again, we have a half of an O2, and we have 1 O2 gives us 3 halves O2. Yeah? And we end up with 2 NO2, 2 NO2, and our intermediates cancel out. Yes? Step 1, we call it KC1. Step 2, we call it KC2. And guess what? For the overall reaction, we call it KC overall. And the only thing to know about it is if you add 2 reactions and you get an overall reaction, you multiply the K values. You don't need to be able to prove it, but this next step here will prove it. Yes? Yes. It's a little the same, it's a little different. Okay, this actual, eat more whenever you have time. I don't think we've done this specific application. Yeah. So it probably looks familiar because it probably looks a lot like, you know, Hess's law, and it looks a lot like reaction mechanisms, and yeah. So if you look at this, when you multiply the 2, you write the KEQ expression for step 1. And you write the KEQ expression for step 2. The intermediates cancel. And you are left with your final products over your final reactants. You combine your like terms and you get Kc of the overall reaction. You don't need to write that down every time. You just need to know that if you can add 2 reactions, then you can multiply their K values to get the final K. Yes? Pardon me? Yeah, sure. Yeah. So our final thing here, when equations are added together to get a net ionic equation, the equilibrium constants must be multiplied to get the overall. So you've got 3 rules. Yes, first one, you flip a reaction, what do you do with Kc? You flip the Kc. Yes? You double a reaction, what do you do to Kc? Raise it to the power of 2. And if you add up a couple reactions to get an overall reaction, what do you do with the Kcs? You multiply them. Those are your 3 rules, and now we can combine those. Ooh, fancy. Consider the following equilibria. We got reaction A, we got KC1, and we got KC2. Give the equilibrium constant for the following reaction in terms of KC1 and KC2. So what you're going to do is you're going to look and you're going to say, what do I have in common here between my reactions 1 and 2 and my reaction 3? Right away, what can I see? What's in common? I have 2 HCl in my reactants, and I need 2 HCl in my reactants. Oh, that looks good. Okay. Now, so it's looking like I can probably just use that first reaction as is because I want the 2 HCl. So I'm just going to leave reaction 1 as it is. In order to get a half S2 in the reactants, what am I going to have to do with my second reaction? I'm going to have to flip it, and I'm going to have to multiply by the entire reaction by, this is a 1, now it's a half. I'm going to have to multiply by. How do we get from 1 to a half? We need to multiply by a half. So looking at those steps, reaction 2, we flip it. So we call this 2 prime. Okay, we have flipped it. And then, and because we've flipped it, KC2 prime is now equal to 1 over KC2. Now we need to have the reaction to get the 1/2 S2. So all the coefficients are times a half, times a half, times a half. Okay, and so that's going to give us 1 over KC2 to the half. Now, that's lovely. Let's look at combining these reactions. This is what we want. We now have reaction 1, which we left as it is, and we have reaction 2, which has been flipped and multiplied by 1/2. Okay, I've just rewritten it here because we're at the top of a new page. It needs to be written again. Now, let's check to see if adding these 2 reactions is actually going to give us our overall reaction. It should. Like 99% of the time, it's going to be that simple. So let's add these 2. H2 cancels with H2. We have 2 HCl, 2 HCl, 1/2 S, 1/2 S. We have Cl2, Cl2, and we have H2S, H2S. Is that reaction 3? Let's look. Are these 2 the same? Yes, they are. So we now have reaction 1 and reaction 2 double prime, and we flipped reaction 2, and we multiplied reaction 2 by a half, so our KC2 is double prime. Okay, and if you want to, you can say it's KC2 to the negative a half. It's up to you. And so we have KC1 times KC2 to the negative a half. Or you could write it as KC1 divided by KC2 to the half. That would also be okay. Is good? Okay, your homework is to do in your equilibrium book, the regular one, do the entropy and enthalpy exercises on pages 118, 119, and 118 to 121. There you go. Ask your physics teacher. Ask all physics teacher.